The chain rule. This is part of chapter 4. It's not on your chapter 3 test. At the same time, it's nice to know it. When things come up on the test, you might be wondering about how to handle these situations, and this will show you all about it. The chain rule, the chain rule, the chain rule. What is it good for? The chain rule is used when finding the derivative of a composition of functions. If you're like, I don't even know what a composition of functions is, the lesson will teach that. You'll find out what a composition of functions is. For example, consider the function f at x equals 3x minus 5 all to the power of 7. Oh my, we can do this actually. We go 3x minus 5, bracket 3x minus 5, bracket 3x minus 5, 7 times, FOIL, 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 all day FOIL. When we were done foiling, the derivative would be easy. Okay? So my job today is to do something and come up with a new rule that turns this disaster into something that's like, oh, that's easy. And it is. Like a lot of the stuff in calculus, this is going to be, when the thing finally lands here, you'd be like, oh, just do that. It's so good. All right, so let me show you. A small investigation. This is where you might start writing if you don't have the notes with you. And you'll probably need a separate sheet of paper, even if you do have the notes with you. The function y equals 3x squared plus 4 squared. And it says some other stuff. And I'll get to the other stuff. I just want to talk about taking the derivative of this thing. Because we can do this one, instead of a power of 7, I've geared it back and gone to a power of 2. And I'm going to go after this thing and hopefully do the job just right. So you have this moment where you go, can we just do this? Is it really that easy? And I'll go, yeah, it really is. Watch. Okay. So if we were going to do this thing with the weapons we have now, we'd have to write out both of these brackets, do the FOIL, okay, and with power of 2, it's actually not that bad. If everything was power of 2, you might be like, oh, I don't need a new rule. It was only because I showed you the example with a power of 7 that you're like, okay, we better check this out and figure out what's going on to give us a chance at power of 7. Okay, so now that's all y steps. Now I need a y prime step, where I actually take the derivative and I get 36x cubed plus 48x squared. At that moment, you should be unimpressed by the result. You're like, okay, so you just did what you said you weren't going to do, which was expand it and take the derivative. You said you have a better way. To show the better way, I got to do a little work on this thing. Yeah, question. 48x, yes, thank you. Great catch. Okay, so the little bit of work I got to do is a little bit of common factoring, which you might have done anyways. I've been trying to nudge towards that you better common factor these things as you go. So I common factor out, let's see, what divides into 36 and also into 48? 12, I guess. 12x. And so then what's left of this is a 3x squared plus 4. And maybe you're unimpressed. Still, but I'm going to do one more little thing because I know what I'm looking for here. And then hopefully you'll see it. I'll write it way up here. Y prime equals that 12x, I'm going to break into two pieces, which you would never do. No one would ever do this. But if I do, I'm going to put the 2 out front. I'm going to put a 3x squared plus 4 there. And the 6x that I just pulled out of there, I just pulled 2 out of the 12x. Now I need a 6x. I'm going to write way over here. Now I'm ready to talk about the easier way. And to help you just a little bit, I'm going to add one more little thing. That bracket has a power of 1 on it. Take a look at this, y equals bracket 3x squared plus 4 squared, and take a look at this, and see if you can see the two things that happened. One is not bad to see it, and one is a little bit more trouble. Where could the two have come from here? Brad? Yeah. It's the power rule. The power rule works on brackets like this. Almost. The 2 was brought down out front, like we've been doing. 3x squared plus 4 stayed as it was. That's the only little quirk in all this. Whatever's inside stays there and gets reduced to power of 1. Good. That's great news. There's an exponent outside. We handle like other exponents we've been doing. Bring it down, reduce by 1. Beautiful. But then this pops out, 6x. Where did the 6x come from? Isaac. Oh yeah, maybe 3 times 4 divided by 2. Yeah, that 3 and that 4 divided by 2. Potentially, that's where it could come from. Doesn't really relate to derivatives per se, though. Is there a place it could have come from that relates to the derivative of what's going on here? Josiah. It's just the derivative of the inside of the brackets. Look at the derivative of 4 is nothing, but the derivative of 3x squared is 6x. And here's the moment. Could it really be that easy? Yeah, it really is that easy. It's the derivative of the outside times the derivative of the inside. That's all. When you got something inside the brackets, you got to multiply by the derivative of that inside. I'm going to do like 7 examples. So you're like, okay, I'm sort of with you. I'm going to do like 7 examples coming up. That's not all they say to do, though. They also say to investigate this. Another way to handle this question, I'll do it in red. And I want to say this again. I don't think anyone would do this question the way I'm about to do it. It's preparing for a different type of question. So this part of it, just go, well, I guess you could do it that way. I guess that works. But I'm trying to get to a really big idea here. You could go, okay, this is a big mess. So what I'm going to do is I'm going to do my let change of variable move that you saw previously. And I'm going to let u equals 3x squared plus 4. It's a really convenient move. Because then what I get is y equals u squared. Isn't that nice? That's what they were saying up here. So I've got 2 different things going on. I got u equals 3x squared plus 4, and I got y equals u squared. And it says, compare dy by dx. Okay, now, finally, Leibniz, we need Leibniz. We need to understand what Leibniz means. It means take the derivative of y, and you better see x as the variable. Okay? Which is what I did here. This is what I did. That y prime there, that's dy by dx. Let me write that in red right beside there. I took the derivative of y, and the important variable when I was doing that derivative was x. Next it says, find dy by du. Take the derivative of y, but the important variable is u. There it is right there. Y equals u squared. I can do that. Dy by du equals 2u. Not particularly difficult. You're unimpressed, I suppose. Then it says also find du by dx. That's this one here. So du by dx equals, let's see, u is 3x squared plus 4, du by dx is 6x. And it says look at the relationship between dy by dx, dy by du, and du by dx. Look at the 3 of them. Well, I've got dy by dx up there. I've got du by dx, and you can see there might be sort of a relationship there. But dy by du doesn't have, it's in u, so how am I supposed to compare that? So let me just go back and write dy by du in terms of x. What's u again? Where is it? You know, when you do change a variable, you're always doing this thing where you're going, where did I put it? It's up here somewhere. There it is. And here comes my highlighter. They want me to compare these 3 things. Dy by dx, purple highlighter. They want me to compare dy by dx, du by dx, and dy by du. If it sounds like I'm saying those really fast, derivative people get really fast at saying these things, like saying dy by dx, dy by du, du by dx. You know, that's the way we talk, really. How do these 3 things compare? It's supposed to be pretty obvious when you stare at them. How does dy by dx compare with dy by du and du by dx? Veronica. Dy by dx is dy by du by ex. This is the awesome part of Leibniz notation. Y prime cannot pull off these kind of tricks. Y prime is awesome. When you're just taking regular derivatives and you know what all the variables are, y prime is a great way to write things. But as soon as things get complicated, Leibniz is way better. And what we've got here now is another way to take derivatives, which is if you want to take the derivative of y with respect to x, but your y is in terms of u, that's okay. Take derivative of y with respect to u, and then multiply du by dx. It's actually what we did here in this part, in the chain rule. It says take the derivative of the outside, keep that all the same, then take the derivative of the inside. This really is the exact same thing, just different notation. You're like, oh, why do you math people do this, where you come up with two different notations for the same thing? It's for different situations. And I'm going to do a bunch of examples and show the two different situations coming up. Okay? Great stuff here. This gets the, geez, I don't know. I wish I had a, oh, pink. We'll go with pink. This gets the pink highlighter. Like, this is fabulous, powerful stuff. It handles all sorts of crazy situations in math and in science and engineering. Whew. Okay, if you, on a scale of 1 to 10, if you're like, okay, derivative of the outside times derivative of the inside, I feel like I'm about a 7 out of 10 on that. I feel like that's pretty good. And this one, you're like, I don't really get that at all. Maybe about a 3 out of 10. We've actually had a great start. We'll take 7 and 3 all day on the first time through this. After the examples, hopefully you're 9 and 5. That's our goal. This stuff you should be like, yeah, I got this for sure. And this is like, okay, yeah, I'm kind of getting that a little bit. And that's maybe the best we can do the first time through this. So yeah, Leibniz, we found out dy by dx is dy by du times du by dx. And this is really the statement of the chain rule, although, geez, it's really awful to memorize it like this. F prime at g to the x, and this is saying take the derivative of the outside, but keep the inside in there, then multiply by the derivative of the inside. We'll come back to that later. This is a better way to remember the chain rule when you're first learning. The words is better. Take the derivative of the outer function and multiply it by the derivative of the inner function. That's how most people say it. But technically what we mean is take the derivative of the outer function, evaluate it at the inner function. The inner function stays inside there, then multiply by the derivative of the inner. And I'll use both sets of words as I do these examples. And I'm still deciding. I don't want to let this go, but I'm awfully tempted to pull it off your next test because I really got to keep things rolling. So it's still bouncing through my head. What am I going to do? What am I going to do? I'll think about that. Well, I do these examples right here. Starts off pretty nice. These are the ones that I hope the chain rule is like, okay, I can do that. That's no problem. F prime at x. Just look at how nasty this thing would be. 3x squared minus 5x plus 4, and you had to do it 3 times, multiply all those brackets, and so on. But now with chain rule, we don't have to do all that. We bring down the 3. But we keep the inside what it is. See? F prime at g at x. That g at x stays inside. So this stays inside. So derivative of the outside is what we usually say in words. But then there's one more thing. If it was just that easy, I would have taught it to you on Power Rule Day. But there's one more thing to this. And what's the other thing I have to do here? Josiah. Derivative of the inside, okay? And it's multiplied by derivative of the inside, which is great news because this thing stays factored. It's wonderful like that. Chain rule keeps it all factored together. There's no adds and subtracts and have to multiply out the brackets like quotient rule and product rule come up with. Chain rule just goes, yeah, there you go, done. There can be other factoring to do after you're done that, but often not. Often that's it. That's chain rule. Derivative of the outside, evaluate it at the inside. So f prime at g at x times g prime. Or if you want, dy by dx, or dy by du times du by dx. This is the dy by du. Take the derivative of y, but act as if this is all one thing. Then take the derivative of the inside. So I'm trying to do all those things all at once. If you're confused at all, right now, it's totally great If you all you understand is, okay, derivative of the outside times derivative of the inside. I got that. If you're there, the rest of it will come. Okay. Another. This is not ready to do the chain rule on. I can't jump right to g prime. I first got to take g at x and write it in a more derivative-friendly form. Square roots are like power 1/2. No, they're not are like power 1/2. Square roots are power 1/2. And this one would be impossible to do without chain rule, because there's no way to expand these brackets out and get yourself over to power rule. Chain rule, though, says derivative of the outside. So I just act like this is all one thing. And if you're trying to access these u's, what I sort of do, ignore this if it hurts you, if it blows your brain out. That whole thing is u. You know, I write it on there enough that you can completely ignore the u if you're not there yet. And the idea is I'm just going to take the derivative of that whole inside, outside there and just go, okay, 1/2, keep all that the same, and reduce that power by 1. If that's completely weird, well, you know what you're doing Thanksgiving weekend, is you got to do a lot of practice on power rule to get yourself up to speed so that you can do chain rule. But to explain it again, I brought the exponent down and multiplied by it, and then I reduced the exponent by 1. But that's not all. Then I got to take the derivative of the inside. I did dy by du. I kept the u in there. Now I got to go inside and take the derivative of the inside, which is 12x squared plus 2. 12x squared plus 2. That's the du by dx. That's the derivative of the inside. You can think of u as the inside. dy by du is take the derivative of the y, but keep the inside the same, and then take the derivative of u when you get there. Calculus is over at that point. I got some algebra to do, and this is where the questions usually come in. I'm going to get the last few steps down, let you absorb them all, and then come at me with questions after all that's done. These are the steps that are probably going to cause you the most difficulty. Chain rule in and itself, again, like some of the other things you've learned in calculus, chain rule by itself is not particularly difficult. The idea that, like, if all there was to it was derivative of the outside times derivative of the inside, I probably didn't need you to come in today. I could probably just emailed that out. Chain rule, derivative of the outside times derivative of the inside. This algebra is what you came in to see today. So if you have questions on that algebra, now's a great time to ask them, because that's really reaching out and pushing your algebra limits there. Which step do you want to talk about? Marie, which step do you want to talk about? Yeah, as much as you can. I put a big note at the top of the test. I say, express your answer with no negative exponents and with no rational exponents, no fractions as the exponents. That's my hint to it. And then I'm going to say on this test, any common factoring you can do. Those are the big three. Get rid of negative exponents, get rid of fraction exponents, and common factor if possible. That'll be good enough for now. The homework might go farther if this thing, let's say this thing factored. But on the test, I'll be sort of lenient about that so far. Now, there's a reason why we're like that. You're like, well, why do you care about negative exponents or fraction? It's really going to matter really, really soon. I'm telling you, that story is almost complete where you're going to go, oh no, I can't leave that with a negative. You're going to learn why it is we don't want these negative exponents and these rational exponents. And we've been working on that and forcing that on you for years. Now, soon you're going to find out why it is. Questions about the steps? Well, if you're being honest about the steps, well, chain rule homework's going to go very fast for you. Because normally these are where the problems are. Let me quickly go over it, just in case you're being dishonest. Or less than forthright. This negative 1/2 I dealt with by taking that whole bracket. I knew it had to go to the denominator. Better yet, I did it all at once and said 1/2. I'm going to go back to the square root and get rid of the rational exponent. This 1/2 became 1/2, but a 1 on the top, 1 times something disappears, and I get a 2 there. The 12x squared plus 2 became in the numerator because you could think of that as over 1. Then I saw a common factor of 2 in the numerator, and those 2's canceled, allowing me to get to here. Boy, university solutions. I've been looking at Bella's university solutions. Lots of times they'll go here to there. And they're not being insulting, actually, I don't think. I don't think they're saying, oh, you should know all these steps. Sometimes their solutions are like, you can work all this out. This is where you want to get to. And so you got to go, how did you get from here to here? They didn't get from here to here, actually. They did all this work, and they're going, we're assuming you can get all that detailed figured out. Here's the important step. And so watch out for those solutions, because they're like that, where they just skip steps. Does that help? Explain that one a little bit. On we go. How many do I got to do? A, B. You don't even know. You don't have the notes printed out. Well, some people do. F and then number 2, and then decide if I'm doing that other one. Okay. I'm ready. C. Ooh, sine. The derivative of sine is, and if that's a blank in your brain right now, now's a great time to get that pink highlighted or a little tab, write it down on a side piece of paper, get out a piece of paper, rip it out of your notes and go, must memorize derivative of sine. Not particularly difficult, but it's a really big problem if you haven't memorized it. Yeah? The derivative of sine is cos. And here's where the chain rule comes up in one of these. That's the outer when it comes to sine. The derivative of sine is cos, and I kept the inside the same. If you want, this is the u, cos of u. Now I got to go inside of cos and take the derivative. And so I multiply that by 10x plus 9, which is the derivative of the inside. Now I got to tell you, most people wouldn't write it like that once they get good at these. And I'll go, I'll make a sort of a, what's the emoji? He does this face, and he's got the little teeth. No, mine looks like a pumpkin. You know the emoji I'm talking about? That's like, yeah? Here's what you'll do normally with sine and cos to avoid causing yourself trouble. It's almost exactly the same. You'll go f prime at x equals, and you'll go, oh, sine, cos. Okay, let me just make a little room here. Yes? Same thing, but I'm going, okay, anything that comes next is going out front. Sine and cos is usually the last on the list because this gets confusing. Is this cos of this times this, or is it cos of this times this? You know what I mean? Like, it's a little confusing. But if you write this out here, then you don't have those kind of problems. You're saying, no, only the 5x squared plus 9x is inside of cos. Everything else is outside. And so that's a little bit better. And I'll try and draw the emoji do. Oh, that's what I need. See, now he's going to look like just an evil pumpkin. See, I don't like that. Hold on, let's try again. Let's do, oh! Now he really is a pumpkin. Okay, you know what? We're going with the pumpkin. He looks happy, though, doesn't he? Happy but spooky. Actually, it looks like he's got crazy lipstick on, is what he's got there. I'm going to, while you guys are working, I'm going to get those emojis, email them to myself, and get them along here where I can just drag them out. You know? That'd be good. So, Todd, you're shockingly bad at drawing. You'd think in 47 years we would have got past JK here. You know, like you think you might have made some progress there. Nothing. No progress whatsoever. My 4-year-old draws better than I do. Any questions about that one? Derivative of the outside times derivative of the inside. Oh, here we go. Here we go. X to the power 4 minus 6 times cos squared x. Okay, cos squared x causes people no end of heartache. Question? Inside the brackets, you can common factor inside a cos, and with everything I've said so far, you might be like, shouldn't we always common factor? When it's inside a cos like that, it generally doesn't have a big advantage because there's nothing it can go cancel with. That's the big deal about common factoring, is finding something you can cancel with. And it's already inside cos, so even if I kind of common factor, it can't really reduce with anything out here. So it's not a huge advantage to do that. Another question. Why isn't that like product rule? She asks a great question. It has to do with this. Sidebar. Sine of, say, 20 degrees, and I'm not even using radians here, so I can really get down to business here and really talk about it. So nothing else is confusing the issue. I didn't use x there. I didn't use radians. We just have sine of 20 degrees. Is when you go 3 times sine of 20 degrees, that does not equal sine of 60 degrees. You see, that doesn't multiply in there. There's something about this number being in there that it's tucked inside of sine, not unlike this. Similar to an example we did earlier. See, the 3x squared plus 1 is tucked inside. This has all got to happen, and then you square it. Whatever is going on here, sine's got to operate on that. So it's not sine times all that stuff. It's sine of all that stuff. And it's very confusing when they start putting a bunch of algebra in there, because then it starts to look like a product rule. And this is why I said don't put stuff out here. Put it out front so you can see, oh, that's a product now. This is a product. This times this. This by itself is not a product. It's sine of all that stuff right there. Does that help? Yeah. That's a slippery one. This one is a product rule because it's all this stuff times cos squared x, but it's worse than that. And I got to help you out here. I'm telling you, if you have trouble with any of these, then for the rest of the year, whenever you see cos squared x and have to deal with it, I would suggest writing cos squared x like this. That's what we really mean when we write cos squared x. We mean take cos of x, evaluate that, and then square it. Now, this is a product rule. I'm going to do that little underline thing. It's this function times that function. And that function has got some problems with it because it's got chain rule in there. And that's where we're headed to, actually, later today's lesson called tough derivatives. I'll just fast forward here. That's what's up this afternoon. Product inside of quotient with chains all the way through. Yeah? Dun, 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 Afro circus, Afro circus. Yeah, okay. For now, we'll just do a product with a little chain on it. Yeah? Slowly and carefully so you can see all the steps. Product rule. Derivative of the first. X fourth minus 6 is the first. Feel free to use these underline as you're going through these to go, let me just get organized so I know which is the first and which is the second. The underline helps to do that. Derivative of the first, 4x cubed. Derivative of minus 6 is 0. Times the second, plus, that much wasn't too bad actually in this question. Times derivative of the second, which is cos of x squared. This is the chain rule part of this question. So lots going on in your brain. You're thinking product rule, quotient, what's going on here? No, you got to focus. Focus on this and go just the derivative of this. Derivative of the outside, and I'm going to put the power of 1 on there so you can really see it, times the derivative of the inside. Whew. Now, and I totally have to repeat the whole thing. After I run into a chain rule inside like that, then I got to repeat the whole rule again in my head to remind myself, what was I doing here? I was doing product rule, and I got to start the whole thing over again. Derivative of the first times the second, plus derivative of the second with a chain rule times the first. And then I pause for questions. Oh, there's the first again. There's first, and there's first. Maria. Yeah. Derivative of this thing was 2, bring down the 2, reduce the exponent by 1. Then I had to go inside the brackets and go, okay, now derivative of the inside, and the derivative of cos is negative sine. More questions? My, what a mess. My, what a mess. The common factor weapon, which you may have very little respect for, and actually I was just talking to a grade 10 academic teacher yesterday who was had an angry class that, well, why do you have to put a common factor in it? They were doing this. They were learning about x squared minus 9 and doing difference of squares in that. But then I think the one in the test was this. Which they spent forever on and couldn't get it to factor because they missed the common factor. If you just common factor out the 3, it becomes a very easy difference of squares, you see. And so back then the common factor was like, why are you so cruel? Why you got to throw that common factor in there? And when it was in the factoring, or it was in the completing the square section, the common factor was huge. And now it's just monstrous. Watch this move here. After doing, from here on in, starting now, after doing a product rule or a chain rule or a quotient rule, stop and look for common factors because it's going to make your life a little easier. 4, 2, I can pull out a 2. Cos x squared, cos x, I can take out a cos x. Leaving this for, now me personally, and I give this advice to you now, save up your square brackets for when you're common factoring. It'll help organize your brain. Whenever you have common factoring, use a square bracket to go, okay, there. I common factored what was common with both these terms out front. And now what's left of this one? 2x cubed cos x minus x to the 4th minus 6 sine x. Took the 2 out, yes. Took the cos out, left with x 4th minus, yes, okay, everything is good. But maybe it's not good for you. You have questions. Because that's the first time I've done a common factor of that magnitude in the middle of one of these questions. Madison. Explain everything in the square brackets? Were you okay here that I pulled 2 cos x? I could see a 2 in both. I could see a cos in both. So then I looked and said, okay, what's left of this term once I pull out 2 cos x? What's left of the 4? A 2. What's left of the x cubed? Oh, I didn't pull any x's out, so x cubed still there. And I took one of the cos x's out, so I need one more cos x. Second bracket, what's left of this thing? I took out the 2, I took out the cos x, and I was left with just this here. And I'm going to do what I said is that I'm going to try and pull polynomials out in front of sine. So really, I just kept those 2 things and wrote them in a different order. And it became negative because of the negative there. Does that help? For now, when you're seeing these, following them is the most important thing. Knowing that you could do them. No, that's why I got more examples. You want to see this a few times. And that's why I got a big lesson on tougher derivatives this afternoon where I go, let's do it again. Let's try the common factoring again. Let's try the common factoring again. Because it's not, I got to tell you, it's not quite as bad as it looks. There's some things in math that are like, okay, that's tough. This really isn't, this common factoring. You just got to see it a few times. Questions? More time? Oh, it looks horrific, doesn't it? But the common factoring really deals with this, and really, because it takes a whole bunch of stuff out of it and makes what's left a lot simpler. And it'll just get more so like that. This one, it's not bad showing off common factor, but the ones that are coming later are like, oh, the common factor completely bails us out there. Not only that, it's going to common factor and cancel probably, and just completely simplify everything that's going on. Why are we allowed to leave? She says, why don't you not add or subtract, multiply this bracket out? You said yesterday that you could multiply it out. And she's right, she's busted me on that. I know something you don't, which is it's not going to result in anything. I can see that there's no simplification that's going to happen there, but you'd be right to do it. I only didn't do it because I sort of knew what was about to happen, and so I will do it here to keep to that. Geez, I hope you don't think it's a rule when I say you have to multiply out the brackets when it's add and subtract. It's more of like a 98% guideline. Like it's almost always the right thing to do. So here I get negative x to the 4 sine x, and I get a plus 6 sine x. But you see how it didn't really result, because of the sines and coses, it didn't really result in me achieving much more there. So maybe these are better together as all one sine x. That's where the 98% rule comes in. But you're absolutely right. From the way I've been saying it, you definitely should have multiplied out those brackets. Great questions. You're asking the right questions. Okay, we really got to talk about this. Because after everything that's happened, it would be awfully tempting to do this as a quotient rule. Your brain will get trained where you go, anytime I see that fraction, I'm going quotient rule. Derivative of the top times the bottom minus derivative of the bottom times the top, all the bottom squared. Here I go. But because of the constant nature of the numerator, there is a better way. Is to write this as f at x equals 3 times 2x minus 1 to the negative 5. When that numerator is a constant, don't use quotient rule. Sorry. You can use quotient rule. And I'm going to do it in a second here. I'm going to go over here. Let's see. Actually, I'm going to really exaggerate it to really make my point here. Let me just reserve a little room for quotient rule over here. But let me do a chain rule when it's a constant number at the top there. F prime at x equals negative 15, 2x minus 1 to the negative 6 times 2. And so I get f prime at x. I'm trying to prove I can do it in 2 steps here. Negative 30 over 2x minus 1 to the 6th. If you're not quite following those steps, I'm going to come back and explain those steps in a second. Well, what I want you to notice is how many lines that took me to do that. I did derivative of the outside times the inside, times the derivative of the inside, and then I just simplified things up a little bit. If you did it as quotient rule, here it comes. F prime at x. Derivative of the top times the bottom minus derivative of the bottom times the top all over the bottom squared. You see how things get completely out of hand? And sometimes they're going to get completely out of hand. There's going to be no choice, but not when there's just a constant up at the top there. You don't have to do all this when there's a constant up top there. So a little more work here. Let's see, negative 30, 2x minus 1 to the 4 over 2x minus 1 to the 10, and then cancel 6 of those, and I get negative 30 over 2x minus 1/6. This wasn't a lot worse doing the quotient rule, but I hope you see it is worse. And it'll only get more worse the more complicated that function is in the denominator. Now, my point on this particular example was supposed to be constant numbers in the numerator. That's the point of this example. However, in the middle of this, if you're still working your way through chain rule, you may have other questions about what I did here outside of my point of constants in the numerator. And which questions do you have about all that? This was okay? Let me slow it down. Negative 5 came down, multiplied with a negative 15, reduced the power by 1 to negative 6, times the derivative of the inside. 2x minus 1 because it's a negative power. We don't want negative powers in the answer. I pulled it down. Negative 15 times 2 was negative 30 on the top. So that was good. Well, we're cruising then. Oftentimes I have to go through and spend another 5 minutes explaining all that. And if you need that 5 minutes, yes, come and see me. But if for the most part you're like, okay, I got all that, the rest of this, the next chapter is going to go very well because it's just a lot of algebra is what the next chapter really is. Oh yeah, this is the one. This is what we've been warming up for since we left the h's behind. Yes? When we left the h's behind, you might have been angry and you might have said, you waited all this time to tell me I could just bring the power out front and reduce it by 1? I'm like, well, yeah, but don't think your problems are over. Well, that didn't just solve everything on the planet with one little move. There's other things to do here. If the cobwebs are flying through your brain, you might want to shoo them out and tune in for this example. Because if you get it the first time, you sort of get the plan, even this afternoon's lesson isn't going to be that bad to you. I'm going to do the first part very fast. And then I'm going to slow it right back down again. Which rule do I need to start with this one? Because it's not a constant in the top. Got to start with quotient rule. So I'm going to do the first step of quotient rule very, very fast to get off to a great start. First step of quotient rule is draw the top. Really stare at that and make sure you got that down pat. Make sure that's like, yeah, I got that. Because if that's a problem, nothing that I'm going to do next is going to make any sense. Is that step good? Draw to the top. Draw the top times the bottom. Minus. See, that quotient rule where it goes draw the top times the bottom. That times the bottom step is actually nice. You just times the bottom. You just write down whatever the bottom is. Minus the derivative of the bottom. I'm going to do that step fast, but you need then to look at it and see how I did. And I'm going to pause because if you have questions about that, we have to address that because this this example is not about that step. That step by this point in the lesson is supposed to be like, okay, I got that. And if you don't, that's fine, but we need to talk about it if we're ever going to get to the point of example F here. How's that step? That's good. You got that. Okay. So that's the derivative of the bottom times the top. All over the bottom squared. Are you intimidated by that line of algebra? My job over the next couple minutes is to demystify the big mess I've just made here. So, I'm going to call this next step a half step. To really make what I'm about to do work, you have to do this half step. And I'm going to say, don't multiply out brackets or anything like that. Don't get too excited. Just bring together any monomials. I'm using the fancy words now back from grade 9. Just bring together any monomials you see. Just tidy things up. I call it a half step. You're really not going to do much in this step. And what I mean by that is, in this first term, I got a 3 and a 6x. Let's just get all those together. Just the monomials, okay? Just to tidy things up a little bit. It's going to help me to see what's going on. You're going to hear me talk about that half step about 100 times this afternoon when I do the afternoon lesson. Did I get it? Over here, this one doesn't have any monomials. That's not a rule. It's not like, oh, the second one's never going to have any. No. Just look at each one and get the monomials tidied up so that you can see best what's going to happen next. And I almost said what's going to happen next to give it away. But I'm entertaining myself leading up to this big moment that's going to deal with this. Because I said a few minutes ago, someone said, don't you have to multiply those out? And then I answered, I'm like, well, it's not a rule. It's like a 98% rule. And here's where the 2% comes in. Look at that. Can you imagine multiplying that out? Even that bracket's bad enough. But look at this, power 4. There's no way. There's no way. There's no way any math can actually get done if we're going to be spending our time expanding these things out. But there is a powerhouse weapon. And I love to just send this video to the grade 10s and let them see the power of this weapon. And it's the common factor. The common factor will take this question and completely give it the old 1-2 and turn it into something pretty straightforward stuff. Take a look at this giant set of brackets. Start with your monomials. 18x and 4, I can bring out a 2. That's not too exciting. Other questions, that monomial common factor will be bigger and things will be really helpful there, but this one, the monomial common factor wasn't that big. Now look at this. It's so good. I'm just going to highlight them in yellow. You see those two things in there? You're like, isn't that convenient that those appeared in both of them? It wasn't convenient at all. It had to happen. In one of the brackets, I took that thing and reduced the exponent by 1. In the other bracket, I just kept it. It's inherently built into the quotient rule that there'll be this common factor in both sides of it, differing in power by exactly 1. Why exactly 1? Because you took the derivative and you reduced the exponent by 1. There's a lot less magic here than it seems like there is. So my common factor here is 3x squared plus 4. Okay, which do I got 2 over here and I got 3 over there. So how many can I bring out? What's common to both? 2. I can bring 2 out. So I use the lower number. Remember I said that this afternoon. Use the lower number. Because once it gets into negatives and stuff like that, it gets confusing what to take out. The lowest number. But look here. It gets better. I don't like the pink. I feel like the pink you're not going to be able to see through very well. How about the orange? Can you see through the orange? And let me just do the whole explanation again so this demystifies this completely. You're like, oh, isn't that convenient that this crazy polynomial was in both? It's not convenient at all. It's inherently built into the quotient rule. Derivative of the first times the second minus derivative of the second times the first. The first is in both. And the only difference between the two will be one of them will have its exponent changed by 1 because the derivative happened. So it's always going to be the same. Now here, getting ready for this afternoon's lesson, I'm going to say 2x cubed minus 4x plus, slow down dummy, 4x plus 1. I've got power 4, I've got power 3. Which one do I take? The 3 because it's the lower number. Remember that later today. It's going to get a little complicated when it gets into negatives. But for now, it's pretty obvious, lower number. And this is what I was saying in the last example. Then me personally, I open up a big square bracket to go, okay, there's the whole common factor. And then now my job to pick out what's left of these. And wait till you see what's left. It's beautiful what's left of each of these brackets. I took 18x. I took the 2 out. So I got 9x. Look, getting the chills about what's to happen here. 20 years later. Is it only 20 years later? No. 30 years later. Oh no. 30 years later, I still get chills about what's about to happen here. Watch. How many of these got pulled out? 2. All of them. They're all gone. They're done. All that's left is these. How many? 1. Exactly 1. It's perfect. It's beautiful. No exponent 2s to expand out. Nothing. Just exponent 1. And this expansion, you might look at and go, oh, I still got to expand out that brackets. Well, yeah, I know. But compared to that, this is beautiful. Like absolutely beautiful what's left here. Let's check out the other brackets. Take care of that monomial first. Took out 2. It was a 4, so I'm left with 2. I took out 3x squared plus 4 squared. This one was 3x squared plus 4 cubed. It's always going to be power 1. That's left over. Why? Because when we took the derivative, we reduced the exponent by 1, so of course they differ by 1. That's inherently built into the quotient rule. How about 2x cubed minus 4x plus 1? I took out 3. How many was there? 3. They're all gone. They're done. They're out there now. Nothing to worry about. But this one does have a leftover 6x squared minus 4 from the chain rule. And now my 98% rule does kick back in, where inside that bracket, you still have to multiply out the brackets, add and subtract, because this is all polynomial stuff in there. So, my 98% rule from yesterday is, when there's add or subtract between them, you've always got to multiply out the brackets and collect like terms. Yes, I still stick to that, but the comma I'm going to put after now is, but common factor first, to save yourself a lot of headaches. Yeah? Oh, but there's more. I'd like to fit this on one page, so I'm going to just grab that. Does that make that unreadable when I do that? Still good? And I got to try and land this in 2 more steps. I got to do all this expansion here. I'll try and do it in 2 steps. I hope it doesn't confuse you. But there's a better thing that happens here too, though. Look here. You see it? I'll use highlighter to cancel. I'll use green, thin highlighter to cancel. Here it goes. Woo! 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 Tidies up beautifully. And now, as promised, try and do the square brackets in 2 steps, just to fit it on the page. Warning, I'm trying to do this in 2 steps to fit on the page. Any of these expansions you'll probably want to do in 3 steps. So what do I get? 3x squared times 6x squared is 18x fourth times negative 2 is negative 36x to the 4th. And then 3x squared times negative 4 is negative 12x squared times negative 2. I get 24x squared. 4 times 6x squared is 24x squared. Minus 48x squared when I multiply it by negative 2. And 4 times negative 4 is negative 16 plus 32. All over 2x cubed minus 4x plus 1 to the 5. I better check that. I tried to do a FOIL with a common multiple all in one step. How did I do? 18x4, negative 36x4, negative 12x squared, positive 20. Oh, we're off to a good start. 24, negative 48x squared. Yeah, that's right. And negative 6, it might be right. And now, one final step, I think. Square bracket. 18x4, negative 18x to the 4, negative 36x squared, negative 12x squared, negative 60x squared, plus 9x, plus 32. And I got to check that, because I don't know if I nailed it or not. See how I do? 18x4 minus 36x4 is negative 18x4. Okay, x squared, so I did negative 36 plus 24 is negative 12 minus 48. Yeah, that's right. Plus 9x plus 32. I think it's right. it is potential that what's in the square brackets will factor at the end, but it's extremely rare. But after all this steps, that this comes down and nicely factors, usually we're going to need another method to handle that. If your brain's flashing going, wait a minute, what happens if this doesn't factor? How are we supposed to stick on the ice for a little while? A couple chapters. Actually, in March, April, we'll have a lesson where we go, what happens if it doesn't factor? And I got some stuff to show you, okay? Okay, what questions do you have about all that? Besides, really? Like, I can see that as the question. It's like, really, mister? Are you crazy? No, not at all. It's not so bad. It takes a little practice, but it's not so bad. There's tougher things in math than that. It's just a mess. It's tough to look at. I used to accidentally leave it on the board. I'd be teaching grade 12, and I'd accidentally leave it on the board for when the grade 9s come in. Maybe I did it to you when you were in grade 9. You come in and something like this is on the board. It was just to let the grade 9s know, stop your whining and crying about this. No, this. That's all they did. This was grade 10, right? Stop your whining and crying about that because we're going. Yeah? Questions? Tell me. You guys are really good at algebra, and that's probably why you think this is, you're like, okay, yeah. Even if you're looking at going, every step I don't follow exactly, but yeah, I get the gist. I'll work on it, yeah? More time here? Oh, that was the last one. That technically should be in the tougher derivatives lesson. I just threw it in there to sort of warm up a lot of that this afternoon. So if you're like, I was right with you, yeah? Everything was good, and then you blew my brains out. Thanks a lot. You know, that's okay. You got time to work on some of those, and I'll go after this afternoon. Okay, check this out. This is technically a chain rule question as well. Yeah. I don't even know who said that. It's the great thing about the masks. Did I tell you the story about the grade 9s where someone said something back to me and I couldn't figure out who it was and they thought it was hilarious? Because I asked if they thought I was insane for the amount of homework I was giving me. And I heard a whole bunch of no's and one yes. Yeah? So one person said yes. And when they said it, I turned around and I went like this. And they all just went blank face, you know? And so they knew who had said it, but I couldn't figure out who said it because the masks, it kills the directionality and I can't tell who says what, right? Or maybe I'm just old. Maybe that's what it is. I saw a couple eyebrows go up and I go, this was 30 years ago when I learned this. And I saw a couple people's eyebrows go up and I go, whoa, you're older than I thought. Did that give you enough time? Whoever, she passed up. Okay. There's, as much as that's one part of the lesson, the second part of this lesson is this is a chain rule. This is the exact stuff we've been doing, except in a different form. And they want dy by dx, and let me just go through the thinking that will probably happen to you as you do these. You'll write down y equals, hey, pen, please, yes. You'll write down y equals 2u cubed minus 5, and then it says find dy dx, and you're like, dy by dx, that's when you first really start thinking about Leibniz. And it says here, take the derivative of y, and the variable you're looking for is x. And you look at this and go, but it's not x. You know, and Leibniz says, no. Take the derivative with respect to x. And you're like, I gotcha. I understand now. But it's not x. Yeah? And what you could do, you could take this u and sub it in wherever you see u. And you could do it that way. But that's not the beauty part. And I discourage you from doing that because you won't see the beauty of this. The beauty part is saying, if you want to do dy dx, all you do is do dy du. Go ahead and take derivative of y using u as your variable. Do the outer to try and bring it back to what chain law is, but then multiply by the derivative of the inner function. So that's the chain rule. There's outer, there's inner, but just in much more beautiful symbology that allows us to do some powerhouse stuff later. Now it's easy. dy by du. Take the derivative of y, and use u as your variable. Go ahead and use u as your variable. 6u squared. You've done the outer part now. Now go in, dig inside that u and go, okay, now derivative of u with respect to x. And there's u, and I got to multiply that with respect to x. And the only final step is, this said dy by dx, which it says, get this with x's. You know, deal with x's. And I've used the u's to get my answer, so then I got to put the u back in there. And I've made a little mistake. I see it. Derivative of 3x squared. Did I make that exact same mistake earlier? Not reduce the power? I think I did. 3x squared, that's a 6x minus 5. Doing all this crazy calculus. I screwed up on derivative of 3x squared. That's funny. Okay, now if you're really with me, you're like, oh, so that's just chain rule. You know, you just went, you brought the 2 down, reduced the power by 1, and then multiplied by the inside. So it really is the exact same thing, but it's just set up a little different. And I encourage you, when you get to these questions, don't cheat and put the thing in there, unless you really, really have to, because it is going somewhere. There is a plan with this dy by du by dx stuff. So don't give up on it yet, just because in these particular examples, you've got a way that you could handle this. Get ready for these type of things. If you have to, do it with putting the u in first to make sure you can get the answer, and then try these out, because this really is beauty when you can land it. Questions on that? There's just a few of those in the homework. Okay. I'm going to put this on my list, this last page. Slope of parametrized curves. I'm going to move into the second half. I've got to review parametrization anyways, getting you ready for the AP exam and so on, and getting ready for your final exam. So on that day, I'll put this in there. So if you get to ones that have X's and T's in the homework, I'm going to try and, when I sit down, find them on the list for you. But when you run into these, skip over them. We'll get back to them probably about April the 20th, is what my brain tells me. Okay? Was that the last part of that lesson? Yes, that was the last page. Questions for me, Simon? Go back to the last example, he says. This